All right, so the goal of this video is to look at and create partial fractions. And so partial fractions take an expression and basically break it down and undo finding a common denominator. And so maybe to kind of link it to something you do know, at some point when you first learned fractions, you would have, let's say, like 2 thirds plus 1/4, and you needed to add those. Well, you'd find a common denominator, and between 3 and 4, you get 12. So you could say, oh, well, 2/3 is the same thing as 8/12, and 1/4 is the same thing as 3/12. And then you could now add them, right? 8 plus 3 over 12, or 11/12. And, similarly, maybe as you moved on through algebra, maybe, you have like an expression like 4 over x plus 3 over x minus 4. And you wanted to add those together. So again, you needed to find a common denominator, which would be x times x minus 4. And then this one would get an x minus 4, and this one would get an x. And you could add them together. So that's 4x minus 16 plus 3x over x times x minus 4, which is equal to 7x minus 16 over x squared minus 4x. Okay, now let's go backwards. So let's say we had started with, let's say 7/12 instead of, I'm going to pick a different number. I say, okay, hey, 7/12, I want to know what number of thirds plus what number of fourths could give us 7/12. And, I'm picking thirds and fourths because I know that would break down into, to a common denominator of 12. So I might not know how many thirds and how many fourths I have. But to maybe make this a little bit easier to think about, I could multiply both sides by 12. And when I do that, well, the 12 and the 12 cancel there. So it's just a 7. And then 3 goes into 12 4 times. So it's 4a. And then 4 goes into 12 3 times, 3b. Now, it's only one equation, but it kind of maybe seems easier to find. I could say, oh, well, if a is 1 and b is 1, I know 3 plus 4 is 7. So if a is 1 and b is 1, that's a true statement. So one of the solutions could be 1/3 plus 1/4. And, maybe depending on the nature of your problem, there are other solutions, but this one seems to work perfectly. So that idea of multiplying by 12, because that was the common denominator, is sort of our goal when we start looking at rational expressions that we have to break down. Like something like this first example, 3x over x plus 2 times x minus 1. I want to know, if I were to have gone backwards, like almost like saying, hey, what would this have been? What problem would have given us that final result? I would want to know, well, how many x plus 2s were there? And how many x minus 1s are there? And this is really tough to look at by inspection. But if we do something like we did up here, where we multiply by the common denominator, that might make this equation a little bit more manageable. So we're going to multiply both sides by the common denominator. And so this whole unit will get multiplied to the left side of the equation, which is nice because it's going to cancel the denominator, and then multiply to here and to there. So let's see what we get. So we get 3x, because that had canceled, equals a times, well, the x plus 2 will cancel the x plus 2, so you get an x minus 1. And now the b will cancel, the x minus 1s will cancel, so with the b, you get x plus 2. Now, this equation, again, it's equivalent to the given equation, but maybe it's a little bit easier to manage. And the other thing I want to make a reference to is that although there are 3 unknowns, there's technically only one variable. The only variable is x. X can vary. A and B are going to be fixed. And, this is maybe the first time we're going to actually think about the word variable, like, the word variable. A lot of times we just stood for an unknown, but this time variable is going to mean like it can vary. Like not only is it unknown, but it has to be true for every x. Where A and B will be fixed unknown. So x is a variable unknown, where A and B are fixed unknowns. And so this equation has to be true for any x that you pick. So I say, let's pick some smart x's. Okay, so what are some smart x's to pick? One of the smart x's to pick is 1. And you might say, well, why? Why should I pick x equals 1? Well, right there. Right? If you let x equal 1, that becomes a 0. So now we can sort of isolate our unknown b. Since this equation has to be true for every x, if we pick strategically, right? If we pick smartly, we'll be able to isolate the a and the b. So that means if x is 1, that means I have to actually do like 3 times 1 equals a times 0. Plus b times 1 plus 2 is 3. So I want you to write down like which x you're choosing, and then you kind of put like an arrow, because it's not an equal sign because the equation itself has an equal sign, but you're just basically saying that when x is 1, this implies my equation now becomes this, or 3 equals 3b, therefore b is 1, which is really, really nice. The other smart value of x, now that you kind of can see what we're trying to do here, would be choosing x to be -2. So let's let x equal -2. And again, just show me that, okay, let x equal -2. And then let's see, what do we get? Well, the left side, 3 times -2, equals a times -2 minus 1 plus b times 0. Or -6 equals -3a plus 0. So then if I solve that, it looks like a is equal to 2. So I found the two values that are the fixed unknowns. So then how do I answer this question when it says, if you look at the directions, the very beginning, it says decompose, right, or rewrite them into their partial fractions. So I'm splitting this up into the parts, or the partial fractions. So I know my a and I know my b, and there we go. So I'm looking right here at this step. That's kind of what I broke up into the partial fractions. So now I know a and b. So the value of a, we said was, I think, was it 2 or -2? There it is, 2. So I know a is 2. Let's put my pen and maybe pick green for the final answer. So my a value is 2. So I have 2 over x plus 2, and then plus b, which is 1 over x minus 1. That's it. Like, I'm not solving for anything. I'm just rewriting this expression into its partial fractions in the sum of two parts. And you can check your work. If you were to find a common denominator, it would be the product of x plus 2 times x minus 1. And then you have another one here, right? X plus 2 times x minus 1. And then this side here would need an x minus 1. And this side here would need an x plus 2. And then if you multiply 2x minus 2, and this is plus x plus 2 over, I just left it factored, x plus 2, x minus 1. And then you can see 2x plus x is 3x. The 2's cancel, and you have x plus 2 times x minus 1. So we did get exactly what we started with. We broke this down into its partial fractions. But the partial fractions, that's what I'm after. I'm trying to break them down into to its smaller components. Okay. And it did say the very first type is a non-repeated linear factor. So that means there's only one of them, and the factors are linear. They're not quadratic, they're not cubic. I mean, there's so many different cases, but this first case, the most simple case, is that they don't repeat themselves, but yet they're all linear. Now, another example, example B, you might have to factor first, and that's okay. So we have x plus 23 divided by, so here we're going to create my two factors of x minus 5 and x plus 2. So I've created those factors. Then I'm going to use those as the base over here and say, well, I don't know how many of these I need, and I don't know how many of these I need. And order is not going to matter. Which one comes first doesn't matter. For this addition, that order does not matter. But then I'm going to multiply everything by this common denominator of x minus 5 times x plus 2. And I'm going to distribute that quantity to every component. And the nice thing about the left side is that'll cancel out that. So it's just if x plus 23 equals a. The x minus 5 will cancel that x minus 5, so you'll have an x plus 2 left. And then the x plus 2 will cancel that x plus 2. So you have b times x minus 5. And again, in this equation, which is equivalent to what we started with, there are 3 unknowns, but only one is technically the variable. Remember, x can vary, so you should pick a smart value or pick smart values, but a and b are fixed. Even though these are all unknowns, let's take advantage of the fact that you can choose any x. It varies, and it has to be true for every x that you pick. So a good x to choose, let's let x equal -2. Because when you do that, that gives you a 0 right there. So then we say, okay, well, we still have, this implies that we have -2 plus 23 equals 0. And then -2 minus 5 is -7. So we have b times -7. Well, this is 21 equals -7b. So b is equal to -3. Now, the other nice x we could choose would be 5. So if I choose 5, right there, that'll go to 0. So let's let x equal 5. So now 5 plus 23 is 28. And then 5 plus 2 is 7, so that's 7a plus 0. So that means that a is 4. So I have my a, I have my b. So then I need to go back and reconstruct the partial fractions, which were here, right? So what I'm going to do now is just rewrite that. And maybe I'll choose red or a maroon type of color. There we go. So we said a was 4, so we have 4 divided by x minus 5. Now you could say plus here and say -3 over x plus 2. Or if you wanted to, you could make that a subtraction, like minus, right? Either way is perfectly fine. Okay, so that's our first case. When the denominator factors into linear components and then there is not any repetition. Okay. In the next video, we're going to look at, well, what if there is repetition? Like they will still be linear. Oops. They'll still be linear, but what happens if we have 2 of them? Right. So that's what's on tap for the next video.